So I guess it's time to start. I'm happy to welcome you all at our series in our seminars on machine learning and physics. Today, I'm very happy to introduce Andrea Wulzer, who will tell us about learning in physics from an imperfect machine. Andrea, please.
Thank you. Thank you for the invitation. I guess you can hear me well and also see this super cool pointer, right? So I will report on a set of projects, of papers that we are doing with the aim of designing a model-independent strategy to search for new physics. And I will be more specific in the following slides on what we mean. Some people like to call this more like a model-agnostic search for new physics. And the general idea, in any case, is that in particle physics as well as in many other areas of fundamental science, our priority is to establish the existence of new physical laws that we call new physics. New physical laws that should replace or complement those that we have already established in very predictive and complete reference models. That's the way I would call them during the talk. And in the case of LHC physics, where almost all this is about, this is the standard model of particle physics. So we would like to see new phenomena that cannot be described by this reference model, this new physics. But the way, and this is the main goal, right? But the way in which we proceed in order to explore the data, in order to achieve this goal, is very much, as we say, model dependent. That is to say, it is actually based on searching for new phenomena as they are predicted by some alternative physical models, alternative to the reference model, which is inspired or motivated by structural consideration. Search for supersymmetry, or you search for the Higgs boson successfully in the second case and unsuccessfully for the first case. So the idea of model-independent in physics searches is that one should try to extend the breadth of this data analysis strategy in fundamental physics experiment, taking into account that, well, maybe the right model to be searched for has not yet been constructed and hypothesized. And so we cannot just look for its signatures because we don't know it. And so this method, this strategy that I will describe and that we've been developing in these papers, the last one unfortunately is not out yet, is based on machine learning, from which the title of some of our papers, which have to do with learning new physics from a machine, because this is literally what would happen if this strategy had to succeed. So we will be really learning about the existence of new physics, not from, say, the theory that will tell us what to look for, but from the machine itself, out of which then we will characterize the discrepancy and then eventually really write down the new physical laws. Imperfect is because, as you know, I mean, in all so the predictions that are offered by this reference model, by the standard model, are imperfect. They are subject to uncertainties that you have to take into account, and these are included in our construction in a rather straightforward application of the nuisance parameter, maximum likelihood treatment of nuisance parameters, as is customary to do in this kind of business. And I will tell you about this. Okay, so before going into the details of what. Okay, so before going into the details of our algorithm, of our methodology, let me spend a few slides to explain why we think it's important to work on such model-independent strategies, to develop them. In order to, so let me pose the challenge that we face, okay, in high energy physics, but as I was saying a little bit more generically in fundamental physics. We do observe in high energy physics the transition from a situation where theory guidance was extremely strong, and this is represented here by this bullet, double boson top or Higgs, or even supersymmetry or other scenarios addressing the naturalness problem at the TV scale that were very clear targets. Okay, and that were defining a very clear exploration path that has led, as you know, to the discovery of the Higgs, non-discovery of compelling or expected extensions of the standard model, including the Higgs, which is now instead experimentally confirmed. And as you know, this standard model, including the Higgs, is a putative complete theory, which in principle does not clearly outline, if you want, the features of the new physics that, of course, it's accompanied together with it. And so today, high energy physics should be depicted like an ocean of possibilities that is possible to explore by, again, being guided by theoretical considerations or by experimental facts like dark matter. But this guidance is not strong enough to define a road. It defines multiple directions to be all explored. And just to make things more concrete, so yesterday, okay, we knew exactly what we had to look for in the data. So we had things as powerful as no-lose theorems, like the Higgs no-lose theorem, that will tell us exactly where, okay, what to measure in order to be sure of observing a failure of this reference model that would the standard model, let's say, without the Higgs, before the Higgs discovery. And also, we had compelling, say, beyond the reference models, okay, beyond the standard models, some of which, I mean, the Higgs model itself, which was giving very precise indication of where to look in order to see it, supersymmetry, composite Higgs, and many more. Today, we are exploring the unknown, and of course, the community reacts, okay, to the situation, and clearly, one way to proceed, one important thing is to be, as we see, we are more open-minded in the selection of what we think it's interesting to look for in the data, because we are exploring rather than following a path. But this is not enough. So to me, and probably many other theorists would agree, the right new physics model, the one that really is present in nature, has not yet been formulated. I put it as a possibility, but to me, it's very likely has not been written down. And so we cannot search for it. And we want then to see what's the risk, okay, inherent of this possibility. The right new physics model has not been formulated. So what's wrong with that? So very naively, let's say a string theorist, just for fun, someone very far away from the field would say, but who cares, right? Because if our reference model is capable to offer predictions for all the observables that we can measure in our experiment, then regardless of whether we know where these departures come from, we will just see this in the data if something is new in our data. If there is nothing new, if the LHC is just fully described by the standard model, by the reference model, then well, we don't discover anything, but at least we can sleep happily at night. Thinking just a little bit more, you will realize that this naive answer is right. Essentially, well, for an experiment that is capable to measure only very few, or let's say one observable. Think, for example, the G-2 experiment. Even in that case, actually, you have to be sure that the measurement itself, that the estimator of the measure that you actually do measure, the estimator of the observable, is how it is distributed, okay? But let's say you know it, and it's a Gaussian with standard deviation equal to 1. Then what you can do is that you make your measurement corresponds to this point, you compare it with the prediction of the reference model and the plus or minus 1 sigma band, and you do see a discrepancy. Of course, that's not the reality of the vast majority of modern contemporary particle physics experiments, for sure not the LHC. Our data enable measurement of infinitely many observables, and this infinitely is really infinite. And while on the other hand, we really expect to see new physics in very few of those measurements, okay? We do not expect new physics. We never expected, even before the LHC started, to see departures from the standard model, from the reference model, distributed everywhere in the outcome of the experiment. We know this from previous experiments. We know this from examples of putative new physics model. The Higgs model is a very concrete example that, well, if you, the signatures it will show up as essentially like peaks in diphoton spectrum or in 4-lepton spectrum. All these things are very specific, okay? You will not discover the Higgs model if you search, I don't know, if you look for that lepton pairs production at the LHC. So we really expect that new physics will show up in very few, or let's say only one of these infinitely possible many measurements that you can do, but of course without knowing a priori which one. And so you have to reassess your notion of discrepancy of this measurement, because if you measure 10 more of these observables, as you can do, and so you have to do, those are not observed by new physics. So new physics was affecting only the expected of this, and so already from here you see that this peak, this discrepancy looks much less discrepant, because these are these other statistical fluctuations relative to zero, relative to the central value. And if you measure 100 more, I mean, the situation is even worse. And of course, you will say by high that the discrepancy is washed out to the point that if I remove the marker here, you will not even be able to tell me which one was the actual measurement that, let's say, the string theorist would have interpreted as discrepant. Just for fun, here you have a plot showing how much the expected significance for the exclusion of the reference model goes down as a function of the number of additional measurements you do. Okay, you have one measurement in which the new physics, so the hypothesis that you're testing is different from the reference, right? And you know, like the other one, it's the same hypothesis. And so you see that even a very high level of discrepancy can be washed out if you make enough measurements. This is a manifestation of the well-known Look-Elsewhere effect. So the regular new physics searches in this type of experiments are highly model dependent. So synthetically, we can say that these searches, these ways to inspect the data, they select the observable they measure as the one sensitive to one beyond the standard model. This same observable is selected because it's sensitive to this model, but in general is not going to be sensitive to another BSF model. Okay, so of course there is overlap between possible things. So you may hope that searching for something else you will see the true thing, but this is vastly not guaranteed. And then we should try to accompany regular model-dependent searches with what we call model-independent searches that should be aimed at detecting data departures from this reference model that are not those that emerge from one selected new physics model or a class of models, but generic. How much generic? Well, it really depends on what you do. The full genericity will be to take out the entire output of the LHC and give it to some machine learning algorithm to see if it matches with the standard model prediction. I think this is never going to be possible, but you can try to go as generic as you can. And this is the purpose of what we are indeed doing, okay, in our projects, okay. So I don't mind being interrupted when I speak. So if you have questions, especially if you're not understanding anything, it's most likely my fault. So please interrupt me, but just shout because I don't see chat or other raised hands or anything. Okay. So after this introduction, I will go to explain our idea, our strategy. It is based on the maximum likelihood, frequentist test hypothesis testing. And so if there are Bayesians in the audience, I apologize, but please notice that this is the foundation of the entire LHC statistical practice, and that's the type of physics to which we want to contribute. Okay, so that's an obliged, if you want, methodological choice. So the data that we have in mind, that we target, are the way in which data come out from the LHC, more or less, experiments, more or less. So you do have a set of independent identically distributed measurements, X, of a number of features that essentially you could think to the reconstructed particle momenta for a given set or multiple set of particles, 2 leptons or 4 leptons and jets or MET, in a certain region of interest. So already here you see that I'm not going to be fully model independent because because I have to select, okay, okay, the final state where I'm looking at. There is several final states, but not as many, infinitely as many as there is features, okay, in the multivariate distribution of each of these individual channels, okay. But in any case, this is what I have in mind. Then, of course, it can be extended arbitrarily, but this is the realistic target that we have for our need. So this feature will be distributed. So I will call little n the distribution, if you want, the number distribution normalized to the total number of expected events in the given signal region. I will have, well, I have my reference model, say the standard model, and this one, in line of principle, will give me a prediction of the distribution of the feature X. Okay, clearly it's not going to give me this prediction in an analytic form, of course, right? But conceptually it does. So mathematically it does predict the distribution n of x given R. And if you want to make an hypothesis test, I want to see whether this is favored with respect to something else, which is the alternative distribution, which is n of x given W, where this W are some parameters. So the hypothesis is composite; it depends on parameters, and the test statistic that I have to compute according to Neumann and Pearson, as they teach us in the 30s, is this thing. So when I get the data, I should compute the test statistics, which is the maximum log likelihood ratio, where this is the extended Poisson likelihood with the total number of expected events obtained by integrating the alternative and the total number of expected events obtained as predicted by the standard model, by the reference, and here the say the ratio of distribution ratio, and I have to maximize over all W's, and of course you know very well this, right? You know that if T is large, sorry, if T is small, start from there, it means that well, the data fall very much where this n is big. Okay, it means that they fall very much in the reference distribution. If instead the T is large, it means that after maximizing over W, I can find a point in this W space where the data are much better accommodated by the alternative at some point in W, and so T is big, and this signals new physics. So T is a test statistics on the right side, signaling, if you want, discrepancy in the right side. And in a model-dependent strategy, okay, so what we do one way or another is that we take the alternative distribution to be the one predicted by some given model, new physics MP model. So this model has typically few, or in line of principle could even have zero free parameters. The few free parameters will be like the masses and the cross sections and the couplings that define your really fundamental alternative physical model, okay, alternative physical Lagrangian that you want to compare with the standard model. What we call a model-independent strategy instead is something like this. It's something in which the alternative does not follow right from at least evidently from any concrete model. Okay, it is just written in a parameterized form, and we can use an exponential of some function f just to maintain the thing positive to rescale the reference distribution. Okay, so the W parameters are this thing, are introduced. So the modifications are introduced, of course, locally in the feature space and as a function of these free parameters. And all what we want to ask to f, to this function that parameterizes the alternative, is to be a flexible, okay, function approximant. I insist that it should be something flexible because, of course, if this f is very simple, I know if it's a straight line in some space, then even if there is discrepancy in the data, you will not see, because the maximization will not find the point where the maximum is I, while instead, if this is flexible, it can adapt itself to, I don't know, an anomalous adensation of event at a certain value of x will be fit effectively by this n. So what is the simplest and well-known universal function approximant? Well, the histogram. Okay, so if f indeed is a piecewise constant set of functions, with w being the free parameters of the height in each p, right? Indeed, you can apply this math and discover that you recover the Binet histogram test, right? So the regular strategy of already existing and implemented in various experiments, like music at CMS, model independent new physics search, just to count the number of events that you see in certain bins in the distribution, and you compare it with the Poisson statistics with the prediction of the reference model. And you get it by taking f piecewise constant. So what happens if we take f to be another set of approximate functions? So f in particular being a neural network is our proposal. So our proposal is really nothing fancy, nothing simpler than this. Like you replace, if you come, let's say, from Poisson likelihood binary histogram model independent searches, what you will have to do conceptually is to replace histograms with neural network. And I believe that everybody here agrees that this is a highly motivated attempt because neural networks are effective function approximants in the sense that they are flexible and so that they're flexible but smooth. Okay, so with a relatively limited number of parameters, they are able to describe features that can be very general. Okay, you can have peaks, you can have other shapes. Their virtues in this respect is actually the motivation in several textbooks why we should use neural network, in particular as alternatives to distributions that in particular have a better scaling with the feature dimensionality space, where as you all know, binning becomes exponentially tough. So so this is the idea, and all the rest is calculation to some extent. So we have just to see how to turn the evaluation of T. Okay, so remember, T is the statistics, should be evaluated once we see the data. Okay, these are the actual data as observed in the experiment, and the calculation of T can be turned into a training problem, should be turned into a training problem, right, in order to do something. It will be a supervised training problem, and one of the data sets used for training will, of course, be the data D, the way they are observed. And the other, training set, the other, say the alternative training set in the supervised training, well, we already know, right? It must have something to do with the prediction that the reference model offers, right, of the distribution. And I told you, right, that of course this is not even analytic form. All what we have to represent the behavior of the data, which is normal, let's say, which is the one expected by the reference model, is some sort of reference sample, which is exactly the same thing, which in a regular model dependent or in a regular LAC analysis you would call the background sample. Okay, so what we need is a reference sample or background sample that we should be sure it's distributed according to the prediction of the reference model. So it's synthetic instances of the same feature X, okay, of which you can have a certain variable number that in principle you can choose, that follows this n of x given R distribution, and that is either obtained by first principle Monte Carlo generator, or it can be obtained by data collected in say control region, which is translated then to the signal region. So the tail origin of this reference model is of course irrelevant for the argument. And the math, okay, actually gives rise to the need of this reference sample in a quite weird way, in the sense that if you just plug in the formula for T, our neural network parameterization for the alternative distribution, you find out that the only place where you need actually this reference model is in a seemingly trivial thing, which is the total number of events as expected in the alternative hypothesis n of w, which is this integral that of course you can compute only by approximating as a Monte Carlo sum. Okay, some Monte Carlo sum over the reference, which provides this very simple formula. Notice that in this simple formula, I'm reading this as equal rather than approximately equal, and I can do this only provided that the size of the reference sample is large, and in particular, it should be much larger than the expected data statistics, and it may not be trivial to get such large sample for a real LAC analysis. Okay, right. I will come back on this in a second. In some slides. So now the math gives a very simple answer, right? The maximization is turned into a minimization of this thing into square bracket, which you see as the form of a loss function. Okay, so as promised, the problem will be solved by supervised training with label y equal to 1, okay, for the data. Okay, the data D, which gives this contribution F, which comes from here to the loss, while for y equal to 0, you do have turn on this other contribution, which is the one that is coming from this integral minus n of I. Okay, so it's a quite weird loss. We call it maximum likelihood loss just because we derived it from this math, starting from the maximum likelihood Neumann-Pearson T. Okay, so how then the algorithm works is just to repeat what I just said. So the idea is that in order to compute T, what you have to do is to take your data sample, totally unbind the sample, just it's represented here in a binned form. You have your reference sample that you get to get somewhere, and then you train a network D versus R, okay? And what you get at the end, well, it's the minimum of the loss, minus 2 times the minimum of the loss by the previous formula gives me the test statistics, so something that indicates if the data are discrepant or not. But of course, you can also use the F, the training network itself, which is by definition, okay, is the one that maximizes the likelihood, okay, and then is the maximum likelihood estimator of the distribution log ratio. Okay, remember the definition here. So the log of the ratio of this and that, the best fit alternative, the best fit point in the alternative space is provided by this F, and this can have interesting application. For example, in this case, you see there is an adensation of event around 0.8, and this is shown up by the network telling us that there is something weird going on here. So it can be used if you see some discrepancy to identify the region of the phase space where there is this discrepancy. Okay, so let's see briefly. Let's first briefly have a look of what this algorithm gives in concrete. I'm using a very simple example, just a one-dimensional, one feature only, with the reference distribution being an exponential of a certain slope, and so it's this straight line here, the distribution in a logarithmic scale. I'm taking 2,000s of expected total number of events in the background, in the reference hypothesis that I'm calling here background. And then I will also consider one possible, say, new physics model, a sort of resonance. Of course, it's just a Gaussian centered at 0.8, whose expected total number of signal event in addition to this 2,000 is around 10. I call it a peak in the tail, of course, of the distribution. So let's start from the throwing some toys according to the reference hypothesis, and well, you train and you get certain values of t, 8, 6, or 12. You get you also get the trained neural network, which is this log ratio. That you can, in this case, of course, you know the shape, okay, you know the analytic form of the reference distribution, so you just multiply and you get the distribution, the best fit distribution as obtained by the neural network. You see it displays correlation with the statistical fluctuations in the sample. For example, this goes up because there is this anomalous point here. This one here has this weird dip accompanied by some concentration of event, and so there is this feature learned by the network. So the network follows the data, okay, as it should, but it doesn't follow them too closely. If I zoom here, you will see that the network provides a smooth interpolation of, for example, the height of these different bits, okay, which are, on the contrary, subject to their own point-by-point statistical fluctuations that the network doesn't see because they are not significant, okay, according to what the network thinks. Here, for example, it sees something that looks a bit more significant, and indeed, you see that for this particular toy, t is larger. So now we inject this relatively small fraction of events in in the generation of the toys that produce other toys, like these three ones here, where T, you see, is typically larger, where depending, if you look closely to these curves, you will see that depending on how much signal there happens to be in your specific toy, the network is capable or not to reproduce this continuous curve here, okay, to reproduce the existence of a peak, like here and here. Here it doesn't make it, it just make a little shoulder, because indeed here there are few events, and correspondingly the value of T here is smaller than here, but typically larger than the one that you have in the reference, showing, of course, that T is an indicator of agreement or disagreement with the reference distribution. I can quantify performances a little bit better, again, in this simple one-dimensional example. So to do this, the first step is to compute the distribution of T. This just like in any other hypothesis test, I have to compute the distribution of T if data really follow R, the H0, the reference hypothesis, the one I would like to exclude, because it's only by computing this distribution then that I can associate a p-value, okay, as the upper tail probability, a p-value to a certain observation of a certain T in my real experiment. This is computed, I repeat, the strategy has to do with training on each individual data set that you happen to see. So you have to train on each individual toy data set reference distributed, and compute this histogram, which is and then provide like your P of T given R. You also notice, and this will be discussed in some more details later, that this distribution it's very close agreement with the chi-square, with 13 degrees of freedom. This 13 happens to be the number of free parameters, weights, and biases of the very simple 4 neurons network that we use in order to address, to solve this very simple problem. Okay, this is not a coincidence, it has to do with asymptotic formulas that I will discuss later. In blue, you see instead the distribution of T, okay, as computed on again on toys, but on toys which are generated according to the new physics 1 model, this NP model with the transitional peak at 0.8 that I had before, and each time I compute one of these T's, I can compute then now the p-value, okay, using the distribution of T in the reference hypothesis. I can convert it to a Z-score. I'm using the LHC physics definition of the Z-score, the number of sigmas of discrepancy. And then if I want, for example, I can compute the median of this Z-score to give a quantitative measure of how well this strategy is able to see new physics 1 model. Okay. So this is a plot, this is a scatter plot showing how much discrepancy we see for different random toys of this, again, this NP1 little peak. The scatter plot has on this y-axis what we do see, and on the x-axis, as we always often do in our papers, so we have something that we call, in this case, the ideal Z-score. Details are not particularly important, but it's a measure of the it's supposed to be an independent measure, a robust measurement of how much the data set is really discrepant. Concretely, in this case, it is the Z-score that each particular data set would have for an hypothesis test which is fully model dependent, and it's fully optimized, Allan Neumann Pearson in this case, for the NP1 for this specific model. Okay, so in these plots, what you see on the x-axis is how much you can, how well you can exclude the standard model if you really hit the right hypothesis, if you really optimize your search for the model that you're looking for. And this should be compared with the Z-score that we get, which instead is not at all optimized for this model nor for any other model. So this one should be smaller than that one, okay, by consistency. So, and we see that there is a correlation, however, between how much the data are easy to see and how much we can see them. We can make another example, like we make a little tilt in the distribution, which does not show as a peak, but as an excess in the tail, and we get a very similar plot, of course, compared with the optimal test for new physics 2. And here you have like a peak in the bulk. Here there are many events, and so even if this is very small, it can be statistically seen, and we can also see it. So this shows essentially that there is a logic behind what we are doing, and that it works in concrete, even if in a very simple example. An interesting thing to notice is that there is a correlation between how much tension we see and how much tension there is to be seen, coming from this. I'm referring to the correlation in each of these individual plots. But there is also a correlation which goes across different models. You can, for example, inspect the median as or the median significance that we do see, and the median significance ideal. You see that they just decrease from one plot to the other, and they decrease together. Okay, so this is to say that the correlation that there is between how much there is to be seen and how much we see does not depend strongly on the nature of new physics. Okay, having here tried, 3 different manifestations of new physics that, well, in one dimension, I don't know how many more things there are. So features in the tail, features in the bulk, and of course, non-localized excess. Okay, good. So now I have to to move clearly towards a more detailed explanation of what we do. Okay, so this was essentially just the basic idea, and then there is a number of more interesting conceptually interesting things. One is the asymptotic formula. Okay. So I already told you about in this plot that we had before, this P of the distribution of T in the reference hypothesis looking like a chi-square. This comes from a reason. This comes from the Wilks-Wald theorem that ensures that provided you compute this T as defined by Neumann and Pearson, and we claim that that's what we are doing with our training algorithm, then you would expect the distribution in reference to be a chi-square with as many degrees of freedom as fit parameters. Okay, so the number of W parameters. And for us, this number of parameters is just the number of free parameters, weights, and biases of the neural network, which was 13 indeed in that plot. Of course, the Wilks-Wald theorem is an asymptotic formula, is an asymptotic theorem. It's typically stated as being true, right, as the distribution being a chi-square, provided the statistics is large enough. Enough, what it means, relative to the complexity of the model that is being fitted. Okay, it's experience probably of all of you that if you want to fit a straight line, maybe 10 points are sufficient to be in the asymptotic regime for everything, right? While if you want to fit something which has 10 parameters, you will probably with 10 points, which we will for sure not be in this asymptotic regime. Okay, so given that in our problem the statistics is fixed because it is provided by the number of data, okay, which enters, which is really, so we cannot change it, right? We can phrase the same the other way around. So we will get a chi-square with this right number of degrees of freedom, provided the model we fit is simple enough for a given statistics of the data. So it's not complex. Okay, it's simple as opposite to complex model. So this suggests that what we should do in order to select the neural network model that we use, because until now I've shown you some plots based on some architecture and some hyperparameters, but clearly what we have to do is to design something that also motivates choice for a given architecture or hyperparameters versus the other. So we use this chi-square compatibility as a criterion for model selection. So we would like to have neural network models which are as complex as possible, and then this can mean different things, as many layers as possible, and or as many number of neurons per layer as possible, and also to have a as loose as possible regularization parameters. And for us, the regularization parameters is the value of a weight clipping, so a bound on the total on the absolute value of each individual weight and bias. So for each architecture and for each weight clipping, we can test this chi-square compatibility. The idea is that, as I say, we would like to have the model as complex as possible, as expressive as possible, so regularization parameters as small as possible and network as big as possible, but compatible with chi-square. Why? Because we interpret the violation of this asymptotic formula as the presence so for our network of a sensitivity to low statistics portion of the data set, okay, which means you are not in the high statistics limit. So we think it is a fair interpretation that we call overfitting in our context. Okay. So this is shown here in this, again, referring to this simple one-dimensional example before. So if you start changing this weight clipping for a given architecture, you will find a behavior that, looks very much like a chi-square. It looks still quite close to a chi-square in a quite large region of weight clippings, but you start getting violation if you go to very high weight clipping, and this is probably due to what I was telling you before, the sensitivity to low statistics features, for example, sparse data points, like at the very end of the distribution, that can be fitted in a very sharp feature. If weight clipping is too high, probably this explains this behavior. While if you instead make a weight clipping very, very tight, of course you are restricting the boundaries in the parameter space, and so you do get a violation of Wilks world by the occurrence of a boundary that enters the region, which is statistically fluctuates when you the statistical fluctuation of the estimators of W is pushed to a too small region, and so you do get this behavior. To say that there is not really, at least in this case, a very sharp value of the weight clipping for which this works, but essentially there is a valley, and you can optimize to find a place where the weight clipping, where the distribution is very accurately actually looking like a chi-square. Okay. Okay. So the last topic that I want to cover is actually a very important one towards the implementation of this idea in a realistic context. Okay, if you go beyond really throwing points from in a very simplified problem as I described until now. Okay, so this I'm referring to the fact that the predictions, we call them reference model predictions, but in a regular analysis you will call them the background predictions, are unavoidably imperfect. They are subject to the not complete knowledge, for example, of the part of distribution functions, of the luminosity, of the modeling of the detector response, for example, the scale in the PT of your object. Okay, all these things define imperfections that are described as in regular, say, data analysis strategies as nuisance parameters. So we now have these nuisance parameters nu that are constrained by some sort of prior knowledge, like auxiliary measurements, independent of and that come, if you want, before you do really inspect the data. So they have their own likelihood prior to the experiment. They define a composite reference hypothesis. So the essential difference with what I was describing to you at the beginning is that the standard model, or the reference model, before it was one given hypothesis, one sharp given point in this hypothesis space, now it contains three parameters that are these nuisance, of whose value we're not sure, but we have a likelihood, you see here, coming from the knowledge from some auxiliary measurements here, A here, that constrains its value, but they don't have an infinitely sharpened measured value. Okay, so the math by Neumann and Pearson remains exactly the same. The difference is now that you have to take the log ratio between the maximi of the likelihood so in the denominator, you have the maximum of the likelihood in the reference model, maximized over the parameters, which in this case are the nuisance parameters. Okay, so the maximum in this green region. In the numerator, okay, you do have to maximize over all parameters, okay, which are going to be W and nu of your alternative hypothesis. And your alternative hypothesis, what we want to do is precisely like in the no-nuisance case. It's a local feature space rescaling of the reference distribution, which does depend on nu, such that all things think all this IH depends on nu as well. So it's a rescaling obtained with exponential of a neural network. So the idea is exactly like before. You do have a standard model or reference model effects, which can be described by these possible distributions as a function of nu. Okay, so you span this space nu, and you extend this space by the exponential of a neural network, which provides beyond reference effects, so effects that cannot be accounted for by these nus. The goal, once again, like in the previous discussion, the goal is to compute these test statistics, okay, exactly like before, by to compute these test statistics. Here we need just an additional little step, which has to do with picking up one hypothesis in this green blob, which is the central value reference hypothesis. That is to say, the background for central value nuisance parameters. Okay, central value being the value of the nuisance that best fits the auxiliary likelihood. So prior to the experiments, the most likely, okay, let's say value for nu, we set it to 0, and this defines our central value nuisance reference hypothesis, which we just use to rewrite this formula, okay, by multiplying and dividing by the likelihood in this R0 hypothesis. And so we re-express T as the difference, as you see here, of two terms. The first term, this delta term, is something that has nothing to do, that does not contain any knowledge about possible new physics. Is a purely reference model quantity, is the likelihood ratio between the reference at given nu divided by the reference at this central value simple hypothesis R0 maximized over nu. Okay, this other piece instead is the ratio again to R0 of the likelihood, which will then contain possible new physics incorporated in the neural network. Okay, and our test statistics is the difference between tau and delta, which is the negative of, which is this thing here. Okay, so how we compute these two terms. Okay, so here there would probably be need of another seminar on techniques for likelihood ratio reconstruction that are being developed in the context of likelihood-free inference, for example, to study effective field theory measurements at the LAC. You may have heard about this MadMiner code that does this type of things. So for the purpose of this seminar, just be aware that if you so what you can do, okay, it happens to be possible and not so difficult to do, is to really approximate, okay, compute in an approximate way the log of the ratio of distributions as a function of nu. So you can really have at the very end access, okay, concrete and analytic access of this to this ratio by the way in which we do it, which is an adaptation of these techniques, is that we postulate, we can check that the effect of nuisance is relatively small, such that a Taylor expansion of this log, see here the exponent, okay, the Taylor expansion of the log ratio is a good approximation of the log ratio. The coefficients of this Taylor expansion in nu are functions of the features, are functions of the feature x that we can describe by neural networks. Okay, and so we use this type of ideas that again are at the same purpose in a slightly different context, though, to learn this neural network, to optimize this neural network, having at the very end a representation of this ratio. So we learn the effect of nuisance locally on the distribution. in some sense, this is not much different from what you do in irregular analysis. If you want to have your prediction, I don't know, for the standard model cross-section as a function of the nuisance parameter, you would indeed perform a Taylor expansion, typically stopping at the linear order, right? And infer this distribution by a Monte Carlo at the reference nu equal to 0 and at a different value of nu. Okay, here is not much different than what we do. Just be aware that, of course, in order to learn this ratio, we do need reference data, R0 data, and also reference data with known central value nuisance parameters. Okay, we need to make the nuisance fluctuate, of course, and to have representative Monte Carlos of this, or other, not necessarily Monte Carlo, but representative data set of this situation, and the quality of this reconstruction. Okay, so how well we learn these things can play, depending on the case, can play a crucial role for the success of what we want to do. Okay. Right. So the other term instead is much more similar to the one I was explaining to you at the beginning of this seminar, is obtained by training on the data. In this case, the neural network is the usual one, is the BSM, New Physics Neural Network F, the one which we use to rescale the reference distribution. So again, you will have your data, you will have your reference sample, and you will train it with a loss that is modified from the one that you have seen before. In particular, it includes the ratio, the BSM, sorry, this ratio R, which is the one inherent of the dependence of the nuisance, the effect of nuisance on the reference model, and you will train. You will train actually simultaneously, so you will train to say on the W's of the neural network trainable parameters, but you will also train over the nuisance parameters nu, which have to appear in this form by in an analytic form, which they do, and so you can compute gradients also with respect to these nus together with these W's. Why? Because clearly the maximum here has to be computed over both W and nu. Okay, so this is a slight technicality that is worth mentioning. An important thing, if you want, that it's also worth mentioning is that I repeat that this training, okay, aims at computing this ratio, which has in the denominator only the central value reference hypothesis. So you do need only central value reference samples, and training between the data, exactly like in the case with no nuisance, training among the data versus this central value reference sample. So in particular, you do not need to complicate the procedure by including, say, the reference sample in the training with non-vanishing values of nu. Okay, so this does not makes not more complicated to deal with nuisance, at least from this viewpoint, than to study a problem without nuisance from the viewpoint of BSM network F learning and training. Okay. So if we do all this right, compute right delta and tau, then again, we have our friend Wilks-Wold theorem that, well, without changing, so without reoptimization of the weight clipping, remember I told you that we use the criterion of compatibility with the chi-square in order to select in general the architecture and the weight clipping, but so this we do, if you want, once and for all, in studying the problem in the absence of nuisance. Once that is fixed, it means that the complexity of the network is good enough for the theorem to apply. Then the theorem is going to apply also here, and the theorem here becomes much more useful, if you want, than in the case without nuisance, because the theorem now is saying that the distribution of T, which has to be duly the difference between these two terms, each of them well computed, right? So the distribution of T given in the R nu hypothesis is independent of nu, okay? So it's, for example, it's equal to the one as computed in the central value hypothesis, and it's equal to the chi-square with the same number of degrees of freedom as before, the number of degrees of freedom being the number of W's, the number of free parameters of the neural network. This is of really major, okay, more than major importance for a frequentist test, because in the frequentist statistics, there is no notion of probability of the parameters. So each new value here, it's an equally likely okay, hypothesis of how the actual distribution of the data could be compatibly with the standard model, really compatibly with the reference, right? So the only way to assign a p-value, if this was not the case, would be to compute the distribution of t for all possible values of nu, and then report the p-value either as a function of nu, or you will report for your observation the maximum p-value. Okay, that's strictly the only frequentist way to make a meaningful result, which of course is not feasible from the practical viewpoint, because you have to compute this empirical distribution in a space of nu. It's something impossible, and this is why the LAC, indeed, the exact same methodology, of course, it's employed, right? Nuisance parameters and the Wulzer theorem asymptotic formula to actually deal with nuisance parameters in everyday analysis. So this is the case also for us. So the independence of the test statistic distribution on the true value of the nuisance, on the true value of this nous, under which you can, if you want, generate toys and compute the empirical distribution of t. And this being the case is verified in this slide. In green, you have the distribution of the tau. The tau, remember, is the one that contains new physics, the one that is trained, that contains BSM and that is trained on the data, right? And of course, you will get this type of figures if the central value, the actual central value around which the nuisance are distributed, is away from zero, okay, which is the central value, right? You will see the green curve, right? You will see a distribution which is very much distorted with respect to the chi-square, and of course it depends whether these nuisance are non-vanishing or, like here, vanishing. Okay. Of course, if you just blindly look at tau and compare it with this, you will get a lot of false positives. But if you then look at the blue curve, which is tau minus delta, okay, that one really has to obey the Wulzer theorem, and indeed it looks like this. Okay, it looks like the chi-square. Okay, independently of the point in the nuisance space where I'm throwing toys, so independently on the true value of the nuisance, as you see also here for this. In this case, the underlying nuisance are set at zero, and you have this. I mean, the effect then is less prominent. Where here is where I really worry about. Okay, since time is almost expired, I will just tell you that well, sensitivity to new physics lowers because now we have imperfections as much as it should. In particular, so for new physics like NP2, where the type of nuisance which have to do with scale uncertainty, let's say, can mimic the signal, you do see a significant degradation of performances, both from the viewpoint of our model-independent strategy and from the viewpoint of, let's say, an ideal test designed for NP2. Otherwise, you don't have much degradation. I mean, just the physics-wise, everything works as it should. The nuisance gives you less sensitivity, obviously, but exactly gives you less sensitivity only to problems where the nuisance can actually mimic the putative new physics signal that you're putting in. Okay, so if I read back my abstract, I told you that I would have demonstrated the applicability of the method in a problem that is at the same scale of complexity of a real LAC analysis. And when preparing the slides, I realized that I had so many things to tell you that at the end there will only be one slide of this, and I encourage you to look to our papers and also to the one that is going to appear on the archive soon. Let me just tell you what we did and why we think this is a nearly realistic problem. It is an emulation of two-particle final state at the LAC. An emulation because, well, it's a realistic Monte Carlo for 2 muon production, which then we interpret these muons as different particles, not necessarily mu. Okay, it has a reasonably high dimensionality of the Fisher space, 5. Okay. So reasonably high in comparison with the simple, at least, final state at the LAC. It has systematic uncertainties that we deal with, as explained by nuisance parameters, on the scale and on the scale of the transverse momentum and the efficiency, if you want, normalization, and they are put at the realistic level for corresponding to the case in which the final states are muon or electrons or photons or tau leptons. This last point is a bit more difficult to appreciate, but we do solve this problem with a self-imposed conservative limit on the number of available reference data points. because, as I was anticipating at the beginning, the availability of reference data points from which, for example, you have to throw your reference sample that in principle should be much larger than the data, can be limited in a realistic analysis because detector simulations are long and demanding, or if the sample is coming from data-driven methods, you could have an intrinsic statistical limitation of how many data you get from this control region, which makes things more challenging, including more challenging to learn the effect of nuisance parameters on the distribution by these likelihood-free inspired techniques I was telling you. Of course, the bigger the Monte Carlo, the easier it is. So for all these reasons, we believe that this is a demonstration of something that is really the scale that could be used. We essentially are able to identify viable architectures that, of course, are more complex than the one you have seen in the simple one-dimensional problem, and then they have more degrees of freedom. They comply with the chi-square criterion. Actually, our limitation is more related with resources than with the, but okay. So this viable significantly architecture that work. We do have, of course, demonstrated the possibility of dealing with uncertainties when they are very, very small, like in the muon-like case. We simply don't see anything, right? But if you start making them larger, the scale uncertainty in particular, this is the scale uncertainties on the transfer momentum of electron-like level or tau-like level, you do see a significant effect by the green curve, which then is recovered precisely as I was telling you before by our strategy. And also you can again check whether you can see some putative new physics model. This is another network with I don't know, some Z prime signal, which will produce this green tau, which then will be lowered to the blue because of the delta. But of course, will not be able to wash out the sensitivity because the features of this of the Z primes are too prominent and they cannot be, of course, washed out by the nuisance. Okay, good. So now I'm almost on time. I will just give you a brief outlook of what we have and what we would like to do in the future. So the strategy it's fully defined conceptually, as I think I convinced you, but also methodologically in terms of implementation and in terms of practicalities. Okay. What really will trigger further progress, we believe, is necessarily a full-fledged implementation in a fully realistic final state for the LHC, because we are at the level where we do see where the potential bottlenecks are pretty clear. There are strategies for mitigation or solution, but really one needs to study them in a realistic context. Which one is going to be this realistic final state? 2 leptons, maybe 4 is more interesting, or more exotic final states. But of course, we have to start from somewhere. The expected challenges that one would have to face in this implementation, based on our experience, are listed here. So you will need to have available statistically accurate enough samples for constructing our reference sample. So statistically accurate can be meaning just a large sample, okay, or smart sample. For example, the usage of weighted events for a better modeling of the distribution has not yet been studied systematically, but we have seen already that it plays a major role in the feasibility and the stability of what we are doing. The same type of problem affects the generation of toys that are reference distributed. We want to check the asymptotic formula in the distribution, and so we need toys at least distributed according to the reference. The accurate learning of nuisance likelihood is also related to smaller or not available, so to the availability of reference samples, but not only. And finally, the training execution time, which can become considerable because after we have solved all these problems, we may end up with data samples that are big and that require quite a lot of time to be executed. Notice that all these limited limitations actually are not absolute limitation. They are limit how much luminosity we can handle, how much statistics we can tolerate, how much is the total number of expected events. Because of course, if you make the search with few events, of course, you risk clearly to miss new physics, but you can live with a much smaller reference sample. The toys are smaller, the effect of nuisance is smaller, and so the accuracy in the reconstruction of the nuisance likelihood is less demanding, and also the training time. So I would like also to point out that many of these things are actually not, this type of issues are actually not at all specific of what we want to do, in the sense that faster and smarter Monte Carlo code generators with items listed here, including, for example, generative models for neural networks and better detector and faster detector simulations are recognized as genetic needs for the whole analysis program at the high luminosity LHC. So what we see is just a manifestation of this need in some respect. There is this connection with likelihood-free inference techniques. Here there is again the reference to MapMiner-like of studies about TFT you may have heard about. By learning the effect of nuisance parameters is not conceptually different from learning and actually useful also for studying problems like EFT or matrix element-like methods for parameter inference. And so we believe that these needs can stimulate, but also the solutions we can exploit, as we are already doing developments in this area. For training execution time, maybe the solution is already there, and I want to refer to this paper to appear about the kernel method that will be much faster than training than a neural network, which is a promising direction, okay, for implementation of a strategy in the same spirit as ours, but new physics not being a neural network, but another type of statistical model. Okay, finally, the outlook, we can conclude saying that actually these algorithms are in principle about comparing samples. So they may be useful in other contexts, like comparing Monte Carlo generators or problems of data validation, where you want to make sure that the data collected in a certain week of the year look like those collected in the previous weeks. Of course, the goal is to really do a model-independent physics search at the LHC. I suspect that when and if these techniques makes it to a real analysis, the first outcome will be that somehow we will find plenty of wrong Monte Carlos, because we do see that our way of inspecting the data seems to be more effective than, say, looking at this agreement in 2 or 3 selected distributions. Seems to be more effective, and so it may spot out a number of issues in the Monte Carlos, but maybe it will find new physics as well. Okay, you never know. Thank you for your attention.
Thank you very much for the great talk. Very interesting, complex, and promising. So we have a lot of time for questions. Please raise your hands if you have one. And may I start? May I ask you 2 questions? One is technical and one is some kind of. So considering your first part of the talk, when you formulated your problem as a supervised learning problem, can you tell me what is the typical accuracy of the neural network for distinguishing real data sample and the Monte Carlo data sample and real data sample? Because they look similar, and it will be interesting to know how accurate the neural network is in this task.
What do you mean by accuracy?
So maybe I have got it right. So was this picture you were showing when you formulate the problem in a supervised task?
Yes.
So you label your sample data as 0, so ones, yeah, and the other as vice versa. So you can pose the question: what is the accuracy of your model for such making such a split?
Right. So I think you're trying to refer to how we can quantify this as the goodness. So if we can quantify the goodness of this as a classifier, okay. So yeah, what is the accuracy in really separating the two classes, which will be reference and data. Okay.
Yes.
So overall, this accuracy is going to be extremely poor, right? Look at this figure. You see that when we are searching for new physics really at the LHC, we do not expect to have a dog versus a cat. Okay,
yes,
we really
yes.
expect data that are extremely similar to each other. For example, here they are extremely similar everywhere. Okay, the vast majority of the data is in total agreement. And here, what the classifier will do will essentially give you a not decisive classifier. So will give you, if you look at this, here you see that this, I can see it here. So in the bulk, okay, of the distribution, your classifier will be essentially 0, which means e to the 0. So e to the 0 would be 1/2 in the regular say notation. Okay, so it will be not decisive classifier. Okay, so the way to quantify performances in terms of the efficiency in separating the two samples, I think, is not relevant for assessing the quality of these performances. For example, here, okay, you see, when I see that this is close to 0, right? It's very important that here the neural network doesn't learn anything and that it learns anything to a very good accuracy. Because if the neural network here makes a mistake, okay, so it shifts a little bit this distribution relative to what you have. Here you have so many data that you will start being sensitive to all this data, all these thousands of data that appear here. Okay, so your test statistic will start depending crucially, okay, on a feature, on a region of the feature space, which is irrelevant. So this is just to tell you that the quantification of performances of this as a classifier are very different from those that so you have to quantify the performances of this, thinking completely differently to what you will do if you really wanted to use this as a classifier, event by event based. Okay.
Yeah, this is just very interesting how with low, say, precision, we get nonetheless such a good separation of base and new physics models. Yeah. Yeah,
let's say the precision. So what is very important is that so you do get the modeling of the feature, which needs not to be precise. Okay, that's also another thing. You do not need here to make a regression to this distribution ratio, which is extremely precise. You just have to isolate the region which is discrepant. Okay, from the viewpoint of the usage you want to do of this. You don't want to use it as a classifier, nor you want to use this network as really a regression on the distribution ratio. Okay, what you really want to do is that this network tells you where, okay, the discrepancy is localized, and in turn giving you a big T, right? So I understand. I think yes. So in some sense, I repeat, what is important is that the network is accurate in telling you if there is no new physics, that there is no new physics precisely, that this output is really 0 in the very highly populated region. In this sense, it has to be accurate. What happens in the signal, say, region, needs not to fit this peak precisely.
Mm-hmm. Okay, thank you. And the second question, it sounds very much you might use Gaussian neural networks to solve the same problem. Have you thought on reformulating the problem in this way?
No, we haven't thought of this. So clearly, any idea is welcome. What I was telling at the end is that so if you so the main points were here we will need to make progress at the methodological level from the viewpoint of the training problem is speeding up convergence, and which can be done by changing completely, if you want, the type of model, okay, or it can be done by thinking to optimization of the way we train, which maybe is not optimal. So whatever goes in this direction is in our watch list. If you have some idea, okay, potentially relevant related with Gaussian neural network, I maybe, but so this would so yeah, if you. But because from the viewpoint, let's say from the view from but so we haven't thought about this. So there is space for a lot of new ideas.
Okay, thank you. Looks very promising. So, Grigory, you have a question? Please go ahead.
Andrea, thank you for very interesting, inspiring talk. I have a question. What is the price, the penalty for not knowing the model? For example, if you don't know the standard model and don't know about Higgs, how much more statistics you needed to discover Higgs in this case?
This answer maybe will soon be answered very quantitatively by some of our collaborators, Guy in particular. So that is a very, very interesting question, right? So in general, as I shown here, right, you do pay quite a lot. You do expect to be paying quite a lot, okay? How much you pay is exactly written in this plot, right? For this simple example, knowing precisely the model, knowing precisely that you are searching for this MP1, what does it mean? So it means that, let's say, maybe I take the opportunity to re-explain again this plot. Here, you assume, okay, that you know the model you're searching for, and so you make a test which is optimized to this model. Well, for example, this test, okay, given that the model just consists of a peak around 0.8, will be to cut on this window and throw away all the other data, right? And this will give you a certain expected significance that will be much higher than the one that you have on this other axis. This special plot is more refined than this. We do have really the optimal Neumann-Pearson test constructed by knowing the entire shape of this curve, the entire analytic formula, but the concept is exactly the same. You see that you lose around a couple of sigmas or less, okay, in all cases in this one-dimensional example, okay? So roughly speaking, then of course it depends on it can depend on the example. In particular, in higher dimensionality, it will be a little bit more. You lose always a couple of sigmas. Now, how much this, what this means in terms of luminosity, okay, of effective luminosity that you need to discover something, of course it has to be seen. But you know that for direct search, yeah, let's say this really has to be seen, okay? And in particular, one thing that would be great to study would be to rediscover the Higgs, exactly what you asked, in the regular channels for Higgs discovery, but in a model-independent fashion, and really answer quantitatively to your question, how much luminosity we need. So here for Z prime, like the luminosity scales linearly with the degradation of the Z score, because you really have no event, you just have to see a certain number. So this is a low statistic region, so you can sort of divide it by 2. But in general, it's a very good question.
Thank you. Thank you, Andrea.
So Federica, please ask your question.
Yes, thanks. My question is about overtraining or overfitting, which is a pretty common problem in machine learning.
Mm-hmm.
Do you have such a problem when you train your network, for example? And if so, how do you deal with it? That's something.
Right. Thank you for the question. I just need to clarify a couple of things. So the okay, first of all, let's try to clarify the scale of the problem, right? So, okay, in the realistic, say, type of problem, our networks can be, for example, single hidden layer with 50 neurons, like 5, 51, or we have 3 cases, or 2 layers like 5, 10, 10, 1. So order of hundreds of 3 parameters. A statistics of the data of the order of several 10 thousands of the data D that we use for training, and a higher statistics by a factor of few, 5 or 10, training data in the reference. So our problem, so the parameters of the neural network, so the neural network, I'll say the data are pretty much abundant, okay? So the overfitting, so because, yeah, so what type of overfitting can then occur? The type of overfitting that can occur is in the tail of the distribution. For example, in this one-dimensional example, what you will have, so what the network will see, okay, will be something like this. You will have data which fluctuate, like here, and reference data, okay, against, like here, right, that are much more abundant. This is a lucky example in which we can have a reference sample that is extremely big. So the classical overfitting, in which you like interpolate point by point, will have to fight against this reference. So it's not for free that I develop peaks here that should not be seen by the reference. So overfitting, given that our networks, so I repeat, our networks are relatively small, our training sample is relatively abundant, is not an extremely severe issue. The way in which it manifests itself, at least the way in which the cases in which we observe it and the way in which we try to quantify and mitigate it is by this slide here, by this chi-square compatibility. Essentially, when you do allow your network for a given, say, architecture to have to develop very sharp features by regularization parameters with a very loose regularization parameters, then you can really start seeing that in the tail of the distribution you can develop local peaks, okay, local peaks that really would look like an overfitting classical plot, okay, and the selection of the chi-square for the distribution of the test statistics, okay, removes the occurrence of these peaks. So it removes configuration that are subject to this type of features. Okay. So the overfitting is controlled by this, say, ensemble statistical property. No, it's not controlled on a single training. Okay. Okay, is controlled by the design of regularization hyperparameters. In particular, we just studied the weight tipping, but one could do more general, maybe, and also interesting things in that regard. But it's not controlled on a given training. Okay, it's controlled by selecting the hyperparameters that you use then for training. Okay, and each individual training has no control of overfitting.
Thank you very much.
Micro, please ask a question.
Yeah, hi. First of all, thanks for the really great and interesting talk. I was wondering, for the criterion you have to select the model size. I mean, I understand that it's really great to have a criterion that's based on the null hypothesis itself, because you don't really know what you're looking for.
Yes.
But I'm wondering if you have looked into specific examples, if this criterion also aligns or correlates with the network size that would maximize, let's say, sensitivity or discovery potential or so.
Yeah, good question. So we did quite a number of tests, but probably not enough, in the sense that as of now, I would tell you that essentially doesn't matter. Okay, so that we find a valley of, I mean, more or less in all this valley, maybe excluding this point here, for example, of weight clipping, we do observe very much comparable or similar sensitivities to new physics hypothesis. So I will tell you that this doesn't look to be strikingly important. On the other hand, conceptually, we do always want to have the most possible expressive and complex network, because we do know that will exist models or manifestations of new physics that are too complex to be seen by a very simple network. But we haven't, probably we haven't just worked enough to explore the space of possible models that come to our mind to really find an example where, let's say, it is crucial to have a network with twice more neurons, otherwise you would not see it. So at the moment, my answer is that seems not to be particularly important, but also that one should investigate this point more.
Yeah, thanks. I mean, I could imagine that there's ways to construct examples where maybe a more sensitive test would lean towards more capacity if it's maybe some feature in the tail of the distribution or so. I'm wondering if one could combat that in some way, maybe of some regularization term that takes into account kind of the density of data points in that phase space or so. But yeah, it's definitely a really interesting method, and I'm already thinking about possible applications. So thank you for the great talk.
Yeah, I mean, one example that one could try to really test the capacity, I don't know, like this oscillating signatures, many peak signals that show up at many different points, right? Then clearly you need many parameters to fit all these peaks. Okay, so this is one thing one could try to characterize this mean resonances. Many nearby peaks models, for example, may. But let me just add that then when we go to, say, more realistic scale, okay, at the very end, in terms of neural network architecture, at least, so the weight clipping is selected by this criterion, which makes a difference, right? It's important and it's, but in terms of architecture, our current limitation is computational, in the sense that when since the training is cumbersome, right? It's long. Okay, our trainings are long. Then we making the network bigger and bigger and bigger. We start hitting a problem also because bigger networks take more time to train and a number of things. So at the very end, we, for example, in our last paper that's going out, we selected just the network which is the biggest one we can deal with our self-assigned, well, self-assigned, no, with the computational resources that we decided to use for the paper. So the boundary, the theoretical boundary in how much complex the network has to be for, so the network, so maybe there is a network with 1,000 neurons, which if properly regularized by the weight clipping would still fulfill this criterion, but we cannot use it. Okay, so just to say that the theoretical boundary, we are not sure in which space it is.
Yeah, I mean, that makes sense. Thanks.
And may I ask one more question? Somewhere at the end of the presentation, you had a figure. It was about, I don't not remember what was on y-axis, but it shows dependence on weight clipping for 1.67, something like that. And there are
yes, I go there. Go ahead with your question. I find it. Yeah, there is.
So training epochs and p-value. So it's your neural network is very much sensitive to the exact value of the weight clipping.
Yeah, very good observation. Yes, exactly. Yes.
And suppose I have taken, for example, weight clipping 1.89 and stop training when at the maximum. Would such neural network produce the same result as you have chosen?
Clearly, the answer is that I don't know the specific answer to your question, but let me just tell you few. Just to this KSP value, okay, means the compatibility by a Kolmogorov-Smirnov test with the target chi-square distribution over a quite high number of points, 400 in this case. So this is probably this quantification based on this type of test of compatibility of the chi-square with empirical distribution is a quite, let's say, detailed one. Maybe it's unnecessarily detailed in the sense that that is to say that when you see a Kolmogorov-Smirnov p-value, which is, I don't know, 10 to the minus 5, that doesn't mean that here you will see this distribution sitting outside the screen, okay? So it will move, right? But let's say will still remain within the boundary of what is reasonable, okay? On the other hand, it is absolutely true that in this so nearly realistic problem, we do observe, unlike what I told you being the case in one dimension, we do observe a very strong, as you noticed correctly here, sensitivity of this distribution to the value, the precise value of the weight clipping. The precise reason why this is so, we do not know. We know that this is due to the lack of statistics in the reference sample, in the sense that it seems to us, I mean, like this chi-square is more and more easy to get the more the reference sample is big. And but we don't know very precisely why. Our criterion, so we cannot answer your question because we haven't tried, because our logic has been that we want stable training, okay? So we don't want to do any early stopping. We want to go to the end of training, because we don't want to introduce new parameters like the one related with early stopping. And we, of course, we don't want to stop training for each data point. We want to have a procedure that when you have a toy data set, it works from the end to the beginning. So we set the number of training epochs, in this case, to 1 million, and want to make sure that here, for all toys, we do have reached the plateau. Okay, so this distribution has to stay constant. Yeah, and so our criterion is that we want this plot to look flat, and then we also want this distribution to look like a chi-square. So we haven't explored anything else. Notice that when you want to, for example, probe, like we want to test this network, yeah, you will put it at 200K, but this 200K comes from the collective effect of many toys. So it is possible that if I look at this plot toy by toy, if I am for this configuration, I will maybe see that most of the toys are stabilized, and there is one that is jumping here and there. So I'm not sure we could make an early stopping. So we can define an early stopping based on this plot. So it would be particularly interesting or well defined to stop the training at this maximum. Okay. So I'm not sure we could answer your question. So you see what I'm saying?
Yes, I see. Thank you. But it's one of the ways of reducing the time, the total time. Yeah.
Sure. Obviously, some smart early stopping criterion would be welcome. There are also other minor things you can think to, because the time for each training is something one can live with. But then if you start doing this distribution and checking whether it is a chi-square, you have to redo this training on these toys a zillion of times. Probably what we do also that is not optimal. I mean, one may also probe different values of the weight clipping inside the same training, because if you train with higher weight clipping and then you lower during training, maybe you will see, I mean, there are things that we have in mind, but nothing particularly intelligent that I would like to tell you now. Yeah, but yeah. Mm-hmm. Of course, if there is a neural network model that trains in 50 seconds, like the one that maybe someone will publish at some point soon, then this would solve the issue. But again, this is something that we haven't spent enough work, I think, also on this in the context of neural network and say. But I insist that all these balance, in some sense, are more important because all this training time problem is just, again, limiting how much data we can handle. And until we are not sure that in a realistic analysis we can indeed handle all this data because we have a big reference sample, because we learn the nuisance likelihood, etc., then the problem is a bit, I would say, not marginal, but it's not the first one. But okay, sorry. There are more questions. I'm happy to answer.
Do we have any questions? Well, it seems that there are no more questions. So I would like to thank you once again for the wonderful talk, very inspiring and promising. So thank you very much.
Thank you for the invitation.
Yeah, and goodbye.
Goodbye and good luck for your seminar series.
Thank you very much.